Thank you for coming. A few of you probably remember my last talk that I gave here way back in 2005, and I began the talk by showing this picture of the snow-capped mountains of Nebraska. And I used that to help motivate the importance of the research I was going to talk about that particular day. Now, at least 5 years ago or so, it seemed to go well, so I thought I'd start today's seminar with also a picture. Here's a picture. What we have, this is actually a picture taken from a TV show. That is right. Thank you for pointing that out. So I no longer have to ask the question what TV show that came from. That's okay. So anyway, so we have this doctor here. This is actually Dr. Gaius Baltar. I'm not going to go into the details about what the TV show Battlestar Galactica is about, but at least not all the details. And he's in a laboratory, and he's surrounded by many, many, many vials of blood specimens. Now, this TV show, just to give you a brief synopsis, is about the struggle between humans and a cybernetic life form called Cylons. These Cylons are bad. They want to kill all humans. And in the reimagined version of the sci-fi show Battlestar Galactica, these Cylons can take on a humanoid form that makes them physically indistinguishable from humans. Since these Cylons want to kill humans, it's very important for it to develop a way to determine who is human, who is Cylon. In other words, like a binary trait. And so this doctor here has developed a blood test to make that determination. And you can see that he has kind of a concerned look on his face. That's because now he has to screen 47,905 individuals for whether or not they're human or Cylon, using their blood sample. And the way that he's planning on doing this is to test each specimen individually in a back-to-back manner. So he's going to actually pull out one of those vials, do a test on it. Pull out another vial, do a test on it, and so on. And unfortunately for him, each of these tests take 11 hours apiece to actually complete. So if you translate this into Earth days and Earth years, this would be 60 years it would take for him to complete all the testing that he needs to do. So obviously, there's some problems with how he was originally going to do the tests. He ends up never actually doing the tests. And it's going to take a lot of time and also resources. In fact, he had to get a nuclear warhead from a missile to construct his test for some reason. I'm not for sure why either, even though I'm a Battlestar Galactica fan. But you might be wondering, well, why am I talking about Battlestar Galactica? After all, this is a Department of Statistics seminar. Well, the reason why I start off with this is because there's many similar real-world problems out there. For example, the American Red Cross has to screen about 6 million blood donations per year for a variety of diseases, like HIV, because they want to prevent then the transmission of a disease from a donor to a recipient. University Veterinary Diagnostic Centers have to screen hundreds of thousands of animals per year for diseases as well. A big one in Nebraska right now is something called bovine viral diarrhea virus. And also pharmaceutical companies. They have to screen hundreds of thousands of chemical compounds, sometimes millions, to just come up with a particular set of chemical compounds that they could use, let's say, in the new drug before it even goes to clinical trials. Now, there's a lot of similarities then between these real-world problems with the Battlestar Galactica problem. There's a low prevalence of a binary trait, low prevalence of HIV, for example, in our population. Also, each test is expensive in terms of time it takes, money it costs, resources that are needed to actually do the tests. But there's one important difference. With the Battlestar Galactica problem, the way that doctor was going to do the testing was through individual testing. Again, meaning do a test on one specimen, then do a test on another specimen, and so on. That's not how it's actually done in many real-world problems like these. Instead, what is done is to use group testing. Now, I have a feeling that some of you know what group testing is here, because I'm sure Josh has done a good job educating you all on that. And for those of you who may not know about it, basically what group testing is, it involves combining individual specimens, like those blood samples that we saw, into an overall pooled specimen. So, for example, maybe I have these 4 people here that I want to screen for a particular disease. Well, then I take their specimens, let's say mix them up really, really good, and then from that get a binary result. Let's say a positive or negative test result. I could do it for these 4 people in my population of people I want to screen. I could do it for these 4 people, and so on through the entire population. I could use other group sizes if I wanted to as well. Now, if the group, though, tests negative, that says all individuals are declared negative within that group. So notice it took only 1 test to determine that 4 people don't have a particular disease. Where with individual testing, it took 4 tests to determine that 4 people don't have a disease. Of course, though, a group could test positive. And in that case, there are a variety of ways to actually retest the group members to decode the positives from the negatives. In other words, to find out who in that group caused that group to be positive. And we're going to spend a lot of time on retesting here today. Overall, group testing works well when the trait prevalence, like the probability of having, or the prevalence of HIV in a particular population, is small. Because if it's large, then you're in danger of, let's say, most or even all groups testing positive. And you don't want that to have happen, because you could end up doing more tests than you would with individual testing. So let's talk about retesting. Again, we do this when a group tests positive to decode the negatives from the positives, individuals. Really, probably the first proposal for how to do the retesting was way back in 1943 by Robert Dorfman. He was interested in screening American soldiers for syphilis. And what he said to do was simply retest members of a positive group individually. So if you have a group of size 4, there will be 4 retests. With respect to the Battlestar Galactica problem, just to show you what happens if we were to do this. Since I've watched every single Battlestar Galactica episode, so I guess I could say I've been doing research by watching TV, I know there are 9 Cylons out of 47,905 individuals. And the prevalence is 0.00019. So it's low prevalence. That's why group testing can work in this example. Let's just say that we use a group size of 70. And without showing you all the formulas, the expected number of tests that one would have is about 1,300. The expected length of time to do all that testing is just about 1.5 years. Compare that to the 60 years that we would have had with individual testing. That's the power of group testing. Now, there are many other retesting procedures out there. And if you want a light review of those retesting procedures, you can take a look at my paper that I recently had in Chance about how to do group testing on Battlestar Galactica. And what I concluded was that the smallest expected number of tests that one could actually have in this situation is 256 using a procedure called halving. And the expected length of time to do all those tests, just 117 days. Again, compare that to the 60 years it would have took with individual testing. That's the power of group testing. Yes?
When you calculate the expected length of time, are you assuming that the tests are done continuously over 24 hours, or is that what
Yeah, continuously over 24 hours in a back-to-back manner. That's how Dr. Gaius Baltar was going to do it, so I make that continuous assumption, yes. Still, though, can we do better? Not just in the Battlestar Galactica problem, but can we do better overall in these real-world problems where group testing is used? And that question, yes?
Are you a student of the tests?
Yes. Well, I mean, this Dr. Gaius Baltar was so smart. I mean, he's like the Efron of the Battlestar Galactica world. I figured that he knew what he was doing, and he had perfect tests. So this is what's helped motivate the NIH grant research that Josh and I have been working on for the last few years. And what we came up with the idea of, well, what if we incorporate factors which may influence the disease or, in general, the binary trait status of individuals? And then use these factors then to try to decrease the number of tests that are needed. So, for example, with the American Red Cross, we know that first-time blood donors have a higher prevalence of the disease than repeat donors. So it kind of makes sense that if you have some people that have, let's say, a higher probability of disease, you could somehow use that to reduce then the number of retests that you would need. Veterinary diagnostic centers, through my communications with the one in Nebraska and also Colorado State, if they see something unusual in the specimen, they immediately pull that particular specimen aside and test that individually versus to do it in a group. So in some sense, they're assigning a subjective probability to that particular unusual specimen that they have a higher probability of having a disease, so why don't we test it individually? Drug discovery experiments. Well, perhaps something about the chemical structure of the chemical compounds that you're testing could lead you to believe that has a higher probability of being good, this chemical compound, than another one. So in essence, what we're doing is taking what has traditionally been in group testing in terms of classification of individuals as positive or negative as a homogeneous population where every single individual has the exact same probability of a disease. We're taking that to now a heterogeneous population where every item potentially could have a different probability of having a disease. And yes?
Is there some threshold probability of positivity where it just makes sense to start testing individuals?
Exactly, and that's part of our research. This threshold, we call it the threshold optimal Dorfman, without getting all the details. And once you hit that threshold, well, let's just do individual testing on it. You can talk to Chris McMahon about that, because that's what he's working on, or one of the things he's working on. So how do we get at these probabilities, though? Well, simply estimate them through a binary regression model. You'll see an example of how I do that later on. And thus, then, we've come up with this name for this area called informative retesting, where we're using additional information to guide the retesting of specimens. So we're going to talk about one informative retesting procedure here today. And to introduce it, first I need to talk about some standard retesting procedures. One is called successfully, or what you do is you successfully split positive groups until you get to the positive and negatives. The earliest reference on that I've found is in 1959, but there's still work going on it. And Kim et al. In a Biometrics 2007 paper examined it. An actual application of it, though, appeared in the New England Journal of Medicine in 2005 with respect to Pilcher et al. And they looked at actually applying HIV screening in North Carolina with it. And they said, well, why don't we use an initial group size of 90? And if that tests positive, we're going to simply break it up into 9 groups of size 10. And if one of those subgroups tests positive, well, we're going to further split it up into individual testing. So that's how they successfully split positive groups. A subset of doing this is what we call halving, where now you always do that split into 2 halves. So for example, if I had a initial group of size 8, at step 1, if that tests positive, well, what we're going to do is split into 2 equal size subgroups of size 4. If a particular subgroup tests positive, then if we wanted to, we could go immediately to individual testing for that subgroup for step 3. And we call this a 3-step halving process. Alternatively, if we wanted to, we could continue splitting that group of size 4 into 2 groups of size 2, and then go to individual testing. Simply, that's how it works. Kind of a nice little tree. Well, let's talk about this stuff in a little bit more statistical manner. So let's look at some notation. Let's let G sub Sj be a 1 for a positive group result, a 0 for a negative, where I let the S correspond to the step, and then J tells me, well, which subgroup am I talking about at a particular step? So, for example, G sub 2,1 would be simply the step 2 first subgroup, and G sub 2,2 would be step 2 second subgroup. Unfortunately, and this was alluded to earlier, typically diagnostic tests like an HIV test are not perfect. So we also need to think about what will be the actual true outcome for a test. So let's let G tilde sub Sj now be the true result. So 1 for truly positive, 0 for truly negative. And with that then, we can then define sensitivity and specificity of a particular test. So sensitivity S sub E, it's going to be the probability G sub Sj is equal to 1. In other words, the group tests positive given the group is truly positive. Specificity is going to be the probability the group tests positive given the group is truly, I'm sorry, I said that wrong. Specificity is probability that the group tests negative given that the group is truly negative. Also, we'll let I be the initial group size, so I for a number of individuals. I sub Sj then will be the number of individuals in the jth subgroup at the S step. So for example, I sub 2,1 will be the number of individuals, simply in that are contributing to G21. Then we can also define then the P sub i's as the probability that individual I is truly positive. These are going to be playing a very important role for us. And we're just going to, for now, just think of it in terms of overall one group. So that's why I have my subscript I to go from 1 to capital I. And it's often going to be convenient for us to write these individual probabilities in a vector. So let's call that vector pvec. We'll let T then be the number of tests to decode the initial group. And then we're going to assume each individual is independent, which is a reasonable assumption. Okay. What we like to be able to do is measure the efficiency of a group testing procedure, how good it is, so we can compare it from one procedure to the next. And the way that we can measure the efficiency is simply with the expected value of the number of tests, given our set of these individual probabilities. The lower this expected value is, the better, generally speaking, the procedure is. So let's look at a simple derivation of how to find that with a 3-step halving process. It's not really too difficult. So to begin with here, the expected value t given pvec is 1 for the initial group test that you would always do, plus if that initial group tests positive, then I'm going to have to do 2 more tests. And if a particular subgroup tests then positive, let's say the first subgroup, then I have to do individual testing. So that's where that I sub 2,1 comes from. If the second subgroup tests positive, well, then I have I22 more tests to do. And so, form the sum with then those probabilities. And to find one of these probabilities, let's just take the simplest case first, the probability that the initial group is positive. We need to somehow incorporate then the true outcomes for a particular group, so we write it in terms of these joint probabilities that have the true outcomes for G tilde 1, 1. Then just split stuff up in terms of the conditional probabilities and the marginal probabilities so that we can write it in terms of the sensitivities, the specificities, and these individual probabilities. So for example, this particular probability right here, the probability that the initial group is truly negative is simply the product over all individuals in that group of 1 minus p sub I. That's all. We can look at some of these joint probabilities as well, such as the initial group is positive, the first subgroup is positive, test positive as well. And again, it's just a matter of writing out into all possible, let's say, combinations of what could truly happen with those corresponding groups, and then translating this into conditional probabilities. So you get the sensitivity, specificities in there, and also the individual probabilities. So, for example, the probability that the let me go back. The probability that the initial group is truly positive and that first subgroup is truly positive is 1 minus the product over all individuals that belong, that's why I have this B21 there, that belong to G21 over 1 minus p sub I. We can keep on going to a 4-step procedure, and basically you see this patterns that are starting to form. So again, we have the original one here. We have the 2 times the probability the initial group is positive there. Now, though, since we have an additional halving taking place, we have 2's there. And then finally, to get from step 3 to step 4, we got that step right there, without reading all that to you. So that in general, then, we can actually come up with a nice little, somewhat nice little expression for what this expected value actually ends up being. And, simply, for example, right here, this is just a nice way to write out some of these very long, potentially joint probabilities that you're going to be working with, and the sums there allow you to basically incorporate all those that are needed within the expected value. We can also find then a general expression for this long, big joint probability. And again, you can see some similarities to what we had in the simple case without, again, going through all the details. Now, you can do similar derivations also for the variance. That might be of interest, too. Derivations start getting messier. They're doable, but after a while, it just gets tiresome writing all those equations out, or all those terms out. And so what we actually did was develop a recursive algorithm to take advantage of the hierarchical nature that you see in the halving process that allows us to get the probability mass function, thus, of course, then the moments. And I'm not going to go through the details of that algorithm here today. So far I've been talking about conditional expectations. Well, what about an unconditional mean here? Well, let's let the piece of i's be IID random variables with a mean of p. And to find the expected value of t, well, of course, you just take the expected value of t given p bec. And using the original expression that we had for the expected value of t given p bec, you can basically, I would say, push this outer expectation through to a point where you encounter these piece of I random variables. And by taking advantage of the independence of all these piece of I random variables, you can again come up with a nice little general result. And it's just a matter of keeping track of all your indices and stuff. It's fairly straightforward. Well, let's change gears here a little bit. What if the population was actually homogeneous? Meaning the p size were all equal to, let's say, 1 overall p for all individuals in our group. Well, that's basically what Kim et al. Looked at in their 2007 paper. Well, what one can show is that their expected value that they get conditional on all the p's being equal ends up being our expected value of t. It's kind of an intuitive thing if we have if the piece of i's are IID with a mean of p to begin with. Also, the variance is exactly the same too. And the reason why I bring this up is because it's kind of good to know this if you're, let's say, unable to account for the heterogeneity that might actually be occurring in the population. You get the same results on average. Well, I had this question up earlier. Can we do better? And you might be thinking now after that last slide, no, we can't. I just basically said that you're going to get basically the same thing as what you had with a homogeneous population.
Could
Yes.
I ask that?
Sure.
When you reach the value P, which is your starting time, basically, when you say decoding or the proof, you actually have the possibility that you might not have seen, you might have made a mistake. Because,
that is correct. So you might have a case, let's say the initial group is positive, and then the two subgroups are negative. Well, right now we're just considering a very simple testing algorithm where you would say you stop. Now,
but there's a certain probability that you might have made a wrong decision or something.
Exactly. And there's a variety of ways then to handle that through other kinds of retesting. And what we've been focusing on is more, well, let's get this particular algorithm down. And then if we wanted to account for those cases, well, you can simply add on some more testing. And to some respect, in that way, it kind of gives us a fair comparison from one group testing procedure to the next. So you don't always have to think about, well, what happens if this occurs? What should I do? And now we're basically taking the procedure, let's say the initial way that someone would do this procedure, and just looking at it that way.
Yeah, because what I was thinking is that it's possible that you have a shorter time, expected value to be shorter for your procedure, but then the chances of missing things is also higher.
The what?
The chances that you actually detect that Ian has the disease is a little bit higher because you have less tests. As compared to another procedure, it's actually less a lot of testing, and consequently the chances that you miss somebody.
Well, I mean, I think every procedure out there could reach a point, just thinking off the top of my head, I think every other procedure out there could reach a point where you had a positive first, and then you're basically concluding everyone's negative. And we're just kind of leaving that alone. Yes, we acknowledge that can happen, and retesting could happen. So I guess you could say that what we're proposing here looks at a smaller expected value t than probably what you really want to actually have in terms of if you were to do this in practice, let's say. and take into account exactly the stuff that you were saying, your expected value t would be a little bit higher.
Yeah, it all depends on your ST and SE.
Yeah,
sensitivity.
and you know, typically, of course, SE and SP are usually large numbers close to 1, although as you see in the example, we have an SE of 0.8 in the actual thing that occurs in Nebraska. So, you know, can we do better? Well, we can. Because I kind of glossed over this so far, and that is the fact that we're kind of making this assumption that individuals are put into these different subgroups randomly. Well, what if, though, we control about who goes into what subgroup? And that then leads to our informative retesting procedure that we call ordered halving. Where what we're going to do when we can make this control is that we try to maximize one subgroup's probability of being positive, and then we minimize the other subgroup's probability of being positive. And to do this, let's define a new vector, p ord, where we have our ordered individual probabilities. So p sub 1 would be the smallest. Excuse me. And to see how this ordered halving would work, let's look at a 3-step example. Step 1, test the initial group. Step 2. Let's put the lower risk individuals, as measured by their individual probabilities, into the first subgroup. Put the higher risk individuals then, as measured by their individual probabilities, into that second subgroup. And that basically is what's allowing you then to maximize and minimize what you want. So that what you're hoping is this, is that all the positives end up dropping down to here. And you only have to do individual testing here. Where if you do not make this control, what may happen, at least with a higher probability, is that all your positives will drop down to both subgroups, and then you have to do individual testing for each subgroup, and thus increasing the number of retests that you have to do. And then step 3, do individual testing. If you had a 4-step, 5-step halving procedure, the same thing occurs. We always, work with this ordering to decide who goes into what subgroup. Well, then let's compare then the expected value t given p ord to the expected value t given p vec. So from earlier, then we had this general expression for what the expected value of t given p vec is. And let's just focus in on this part right here. What we can do is rewrite that in terms of some sensitivities and some specificities. You see the number 2 popping up. But take a look at the very end. That's the only place where these individual probabilities arise. So if you order your probabilities then, this is the only place where ordering is going to matter. And the reason why that matters to us is that we maximize that term. You can show that you maximize that term when the piecewise are actually ordered. You can come up with a very similar result with the second term in that, or the third term, I guess, overall, in that expected value, as long as the final subgroup sizes are equal in size. So that then, with that, if the sensitivity is greater than 1 minus specificity, you can actually prove that the expected value of t given p ord is less than or equal to the expected value of t given p vec. In other words, ordered halving is going to do at least as good, most likely better, than, let's say, unordered halving, where you didn't control how you put people in the subgroup. So it's a nice little mathematical result. And well, where does this little condition come in? Well, it comes in right there. Because notice if sensitivity is greater than 1 minus specificity, you get a negative number there. And let me do a little erasing here. Getting a little messy. Then, if this term is negative, look what happens then when you start putting it up here. You get that negative popping up, and thus that's why the expected value t given p vec is lowered if you order the piece. Well, what about just expected value t itself? Well, now, before we took advantage of the fact that p sub i's were independent. Now, piecewise with parentheses around the I are dependent. And so finding this expected value t is a little bit more difficult. And you can work with joint distributions for order statistics to actually find the expected value. But you also need to know then the distribution of the piecewise to begin with. So I can't come up with a nice little general result. The result that I come up with is distribution dependent for the piecewise. So let's look at some comparisons then for different distributions for the piecewise. And we're going to compare expected value t with and without ordering. Here are the 4 distributions. Each of the distributions, or the random variables for the distributions, have a mean of p to make these comparisons fair. And the first distribution is very simple, a degenerate distribution with all probability on one point p. This is the homogeneous case, basically. So all the piecewise are actually equal to p. And based upon what I told you on the previous, or a couple previous slides, this is actually equivalent to unordered halving. So remember that. This is equivalent to unordered halving. Uniform distribution we could work with as well. A beta distribution. This is a right skewed beta distribution, which is reasonable to have. And we've found instances, or most of the instances that we have actually seen for distributions of these p's, or p hats in the end, follow this kind of a setting. And then we'll also look at an extreme case where p sub I is equal to 0 with probability 1 minus p, and p sub I is equal to 1 with a probability of p. This is very unrealistic to actually have happen. But the reason why we do that is because this is going to maximize the variance for the p sub i's. And what you're going to see is that as the variance of the p sub i's grows, ordered halving does better. That's why we're looking at this case. Speaking of the variance, well, obviously it's different for the random variables for the different distributions. Degenerate, of course, has a variance of 0. Extreme would have the highest, and beta is greater than uniform. And we're going to look at some results for, let's say, a hypothetical population of size 10,000. To make things simple, we're going to assume SE and SP, or sensitivity and specificity, are equal to 1. Similar things happen with SE and SP not equal to 1. And here's a table of results. Let's focus in on the top. So P, the overall, you can think of that as the overall prevalence, is actually 0.1. Let's say I do 2 steps, so a 2-step halving process, test the initial group, then drop down to individual testing. This is basically what Dorfman does. Group size of 4, degenerate case, 5938 total tests. Remember there was 10,000 people in this population. This is the expected value. So the expected value of the number of tests is 5938. The true value, of course, could be something different. And notice for the other distributions it's exactly the same. That's because ordering is not going to really help you at all, because you never get to subgroups where ordering would actually occur. You're immediately going to individual testing after the initial group tests positive. If I go to 3 steps, group size of 6, degenerate 5938, but now the uniform goes down. We have expected value of 5880. Beta goes down a little bit further, 5827. Extreme, 5577. So you can see this ordering amongst these expected number of tests that corresponds to the variance of those corresponding distributions. Now, we go to 4-step, group size of 8. We see this continued progression, although the number of tests saved, let's say, grows. And for 5-step, group size of 16, we see the same progression where, again, the number of tests that you save from doing ordering grows as a function of, you could say, the variance in how I've organized the table. We could also look at the case of p equal 0.05. You see somewhat similar results. There are some cases where, like for example here, where that ordering doesn't follow the same pattern, and that's only because the final subgroup sizes could be unequal. And in that particular case, stuff like this can happen, depending upon how you do the final split. But also we see, too, that the benefits from doing ordering also are reduced, too, in terms of the absolute differences in the number of tests compared, let's say, from this middle set of rows to the top set of rows. And again, we could continue to p equal 0.01. similar things happen. But again, you see the benefits, and I kind of like to look at that for the benefits. You see those reduce. So overall, what we see is that for higher prevalences, ordered halving tends to work better. I'll give you a further explanation of why that occurs later. Also, one other comment I want to make is that the group size that was actually chosen here is the one that minimizes the expected value of t for the degenerate case. In other words, for homogeneous population, which corresponds to unordered halving. So actually, ordered halving for these particular distributions could end up actually working better for a different group size. Because I'm looking at the best group size for this column, and I'm saying, okay, let's just make the comparisons on the same group size. So ordered halving could actually do better than what's actually being presented there. Okay, let's actually look at an application then. This involves the infertility prevention program. It's a nationally implemented program for about the last 22 years. And its purpose is to assess and reduce the prevalence of chlamydia and gonorrhea in our population. Every state participates, including South Carolina. So if you want to know more about how South Carolina participates, there's the web address. I will talk about how Nebraska participates in the program. This is how things work. Individuals will visit public health clinics. And they will either have urine or swab specimens collected from them. And all these specimens are then shipped to the Nebraska Public Health Laboratory that's located in Omaha. And they do all the testing then for the entire state there. With each individual, we also have a set of information available, such as clinical observations that are made by, let's say, the doctors that's examining a particular person. We have demographic information, such as where do they live? You know, are they from a rural location, or are they from Omaha? It makes a difference in terms of the overall actually prevalence of the disease. Also, risk behavior. These people have to fill out questionnaires that tell us if they engage in various risky activities. Do they engage in, for example, unprotected sex? Overall, the Nebraska Public Health Laboratory has to do about 30,000 tests for both chlamydia and gonorrhea per year. And they do them in an individual testing manner. Kind of like how Gaius Baltar Balsar Galactica was going to do his testing. Of course, though, we're interested in how would group testing work here. And they're people that we work with at the Nebraska Public Health Laboratory are also interested. Now, yes?
I'm interested in prevalence. I mean, why the interest in individual testing? I mean, can you get good information about prevalence just in, group testing?
Oh, yes, you could. You could, but they still, even right now, they're only doing individual testing for a variety of reasons we can talk about at the end. Basically, I was given a seminar once at Nebraska Medical Center, and they happened to come. The people that we work with happened to come to my talk, and they had heard about this group testing thing, and they were interested. Well, how would it work? And so we got them interested and got them on the grant, and we've been looking at some stuff how it would work. Yes.
So I can see how, like, with urine and blood, how you pool it. With the swab, don't they usually rub it on a plate or something and see if something grows?
To be honest, I'm not for sure exactly how they pull that. I think that's always been a question that we've had. We've just never got around to asking them actually about that. I guess I've always had in my back of my mind how they pull, let's say, mosquitoes that they're testing for West Nile virus, that maybe that they'll, chop it up and then pull it that way. Yeah.
Yeah, I have seen some swab pooling literature in HIV literature, but not in here.
So how would group testing work here? And you don't want to just go out blindly apply group testing to this without having any idea how it would work in the real life situation. So what Josh and I have worked on then is basically a computer simulation first to see how would this work. Would group testing work, and would some of our informative retesting procedures work as well? So what we have here, what we're going to begin with, is just what we refer to as a training data set, where we have, this is just from 2004 data, We do have newer data, but this is what we are using for this particular research right now. 2004 year data, we have known outcomes for the tests. So we know whether or not people are positive or negative. We also have all this extra information that they provide, covariates in other words. We have that information available to us, so how about we just simply fit some logistic regression models. Keep it simple. Let's just say first order logistic regression models from the 2004 data. Then we apply that model to people who were involved in testing in 2005. We ignore their true outcomes for now, and we just get their basically their p hat sub i's. Now, using then their known actual outcomes and our p hats, we're going to simulate how halving would actually be done. And what we're going to do is put individuals into groups chronologically, based upon when their specimen came into the lab, which is a reasonable thing to do. That's most likely how they would actually do it. And then from that, we can generate test responses, assuming the 2005 year results were actually 100% correct. What I mean by that is this. Suppose one positive individual exists in a group. So that group, then that's being tested, the initial group should test positive if the test is correct. But we want to investigate how this is going to work in terms of testing error that occurs. And so what we're going to do is simulate a test response, a binary test response with a probability of S of E, the test sensitivity. And then because this injects a little bit of variability here into our computer simulation, because these sensitivities and specificities, as you will soon see, are numbers that are a little bit less than 1. So there's going to be a little bit of variability that is injected into the simulation. We're going to repeat the process 10 times to account for the simulation variability. And then just simply report then the average number of tests that would result from, let's say, 10 different computer simulations. So we'll look at just one particular case here to keep things simple. Chlamydia, swab specimens, males. 4,081 individuals were tested in 2005. They had a prevalence of 0.13. Sensitivity was 0.925. Specificity of 0.95. This is directly from the Nebraska Public Health Laboratory for the test, the assay that they actually use. Here are some of the results. We'll focus on the first row again. Let's say I use a group of size 8. Dorfman testing would have resulted in, on average, 2984 tests. 3-step halving, unordered, 2633, ordered, 2534. So we are reducing the number of tests, at least a little bit there, 3.77%. 4-step, unordered to ordered, well, you're saving, again, maybe about 80 tests, 3% gain, or 3% reduction, I should say, in tests. And you can keep on looking throughout the table, and sometimes it's just easier to look at the percentage decrease. And you can see that we are moderately reducing the number of tests through ordering here. Okay. In addition to the number of tests, something else is very important I haven't discussed so far, and that is the accuracy of a pooled testing procedure. With that, then, we can define something called the pooling sensitivity, which I will denote by PS sub E. This is the probability that an individual is actually diagnosed as positive going through the entire group testing process, so all steps of halving, let's say, given that the individual is true. One can actually mathematically find this. Simply with a Dorfman's procedure, 2-step halving would be SE squared. For S step, SE to the S power. So you can see these sensitivities are maybe 0.9, 0.95, 0.99. You can see that as you add more steps, you lower the pooling sensitivity. And that is one problem with typically found in group testing. Of course, we want the pooling sensitivity to be as high as possible, as close to 1 as possible. Pooling specificity, PS sub P, probability individual is diagnosed as negative through group testing, given that the individual is truly negative. And then we can kind of turn things around here. The pooling positive predictive value, or the PPV, is the probability the individual is true positive, given that the individual is diagnosed as positive to going through the entire group testing procedure. This number is very important. If you, let's say, for example, you visited a doctor and the doctor says you are positive for some kind of infectious disease. The first thing that you should ask that doctor is, what's the PPPV? Because that will then give you the probability that you are truly positive. Because again, these testing procedures are not perfect. Pulling negative predictive value, PNPV, probability individual, is truly negative, given that the individual is diagnosed as negative through group testing. Okay. Well, let's apply this then to this data from the Nebraska Public Health Laboratory. I've included here for individual testing, so you can call this, if you really wanted to, IPPV. PPV is 0.73. NPV is 0.99. Okay, let's look at how this compares then to using group testing through, again, our computer simulation. So, for example, with Dorfman, we can see that point sensitivity would be 0.925 squared. So we get 0.87. So that drops. But point specificity, look at that. Compared to just doing an individual testing, you get a higher point specificity. You also get a higher point positive predictive value than what you would get under individual testing. These are typical benefits that you see from using group testing. You do get, though, a smaller point negative predictive value. Again, that is typically seen. But really, the reason why I'm looking at this table is to compare ordered halving versus unordered halving. And as you can see, there's really not much difference in terms of overall accuracy. So we moderately reduce the number of tests, but we still get about the same accuracy as doing regular old halving. And you can see that then throughout this table. Okay, so some conclusions then. Ordering moderately reduces the number of tests. Now, I have to admit that before getting into this research, I had expected to see greater benefits than at least what we've seen so far. But still, we're getting some benefits here. And these benefits occur when the variance in the piecewise is larger and also when the overall prevalence is larger. Let's talk about why that occurs through a very simple example. Three-step halving. We'll just make, again, this simple. Sensitivity, specificity equal to 1. Now, if there was if there was 0 positive individuals in that initial group, how many tests would you do? Well, of course, just 1. If there was one positive individual in the initial group, here, that positive, whether you do ordered halving or unordered halving, can only drop down to either here or drop down to here, and then that will lead to individual testing. No matter if you're doing ordered or unordered, so you're still going to do the same number of tests. Let me erase. Well, what would happen, though, if you have 2 or more positives? And I kind of alluded to this earlier. Well, of course, this would test positive. And then, under ordered halving, you'd be more likely than under unordered halving for all the positives to drop down to there and then do individual testing there. Versus with unordered halving, well, you might have some that fall over here, and then you're also left with individual testing there. Notice this is where the big number of tests actually occur, because it's, let's say if you have 5 individuals in G22, well, now you have 5 individual tests to do. So that gives you some intuitive explanation why ordered halving works as well, or works in the cases that it does. Now, still that when we do see small improvements, these can be magnified when very large numbers of individuals are screened. And this often happens in group testing situations. For example, Kim and Hudgens, they had a proposed procedure in 2009 where they saw kind of small benefits from their proposal. But because that they were actually looking at an application where people where 120,000 individuals were screened per year, those small benefits were actually meaningful. A 2% reduction in tests is meaningful in this kind of a situation. Also, the American Red Cross, 6 million per year about that they actually screen for. Actually, they use Dorfman's procedure with groups of size 16. Well, small benefits can be magnified when you're screening so many individuals. Finally, well, where are we going with this in the future? Well, simple extensions. Well, you could have more than one split from a positive group. You could have unequal group sizes within subgroups. seems to be reasonable, and you would probably expect you're going to see even more benefits. We needed to start somewhere, so that's why we started with halving. Also, what we're very interested in looking at further is to improve the accuracy of our testing, of group testing in general, and our testing approaches. And surprisingly, there's been very little research done in an area called back-end screening. Meaning, for example, let's say an initial group tests negative. Well, typically what you would do in a group testing is say, well, all individuals are negative. Well, why don't you just stop and wait a second and think, maybe I could verify that test somehow. Maybe I could somehow retest some of those people that are in that negative, positive group. That's back-end screening. It's been done very rarely in group testing. And by doing that, you're going to bump up your accuracy because you're having to retest some of these people that you originally declared negative. Josh and Chris have come up with a great idea of how to further do this. What they suggest to do is follows. We have ways now that we can come up with an individual's negative predictive value. Again, negative predictive value is the probability that an individual is truly negative given that they went through the entire group testing process and then they were declared negative. So if we look at 1 minus that probability, then we get a measurement of error. And so if somebody has a large 1 minus NPV, that might lead you to believe, maybe my test was wrong and they are actually truly positive. Well, why don't I retest them? By doing that, you should be jacking up your accuracy. And this is going to be the subject of our next NIH grant, our renewal that we're going to hopefully submit in July. So, that's the end of my talk. Are there any questions?
Questions?
So you didn't notice very much improvement with the ordering there. Is that because of logistic regression just didn't explain very much at all?
That's something that I don't think we necessarily have as good of a grasp on in terms of, our procedures is only good as basically our model. But to some respect, what we need to do is get the ordering correct. We don't have to get the p-hats, let's say, correct. As long as we get that ordering correct, we're able to order individuals and proceed. But yes, you would think intuitively, the better that model is, the better you're going to do.
Well, I'm thinking that if you had better p-hats, then you definitely wouldn't want the halving. You want the different group sizes.
Yeah, in fact, I didn't think of that before, but you could see then that getting those p-hats, better, let's say, is going to be more important once we do this little extension in terms of allow unequal group sizes, because you could have some of the groups with the higher individuals, higher probability individuals being very small. So yeah, that's a very good point. Thanks for pointing that out.
I have one last question on the tests themselves. Are the specificity really the same for the individuals being tested in the pooled groups where you deliver?
That is definitely a question, and typically what we've seen is that is an assumption that is made. There's been a little work about let those values vary based upon, let's say, the number of individuals that are actually being tested. So I guess you could say what we're doing is we're making the assumption that the test has been properly calibrated to allow for that. But things get a lot more messier, too, when you allow that thing to change as well. Was there a question over here?
What issue of chance was that you referred to?
It was, I think, the last issue of 2009. Let me give you the full reference. There we go. Let me blow that up for you. It was a fun little project. You don't often get published for doing sci-fi work in statistics, but I'll take it.
I realize your grants with NIH, so you wouldn't be necessarily interested in this, but has there been any application to test using this method to pick out other rare things like fraud and applications?
I don't think I've actually ever seen any group testing applications in those contexts.
Just fraudulent behavior measured by whatever test.
I think it depends upon, can you do some kind of pooling? Can you composite, what the individual items are? Can you composite them into one overall thing to be able to test the pool? And at least off the top of my head, I can't think of particular examples. Maybe you know of.
I can see how you might want to get all the non-suspect people over here, get the small number of suspect individuals, whatever, and then work your ideas. But I just
There's just so many different applications of group testing out there. I mean, to some respect, you're talking about quality control application almost, and there's lots of quality control examples of group testing. I haven't really, we both haven't really explored. I don't think that in too much detail, but I know that they're out there. Yes.
Did you have gold standard data from 2004?
No.
How'd you estimate the EM?
Well, we had to do the following because this was a computer simulation, and there's always assumptions you have to make with any kind of computer simulation. Well, we had to assume, because of what we were doing, we had to assume that those were the true outcomes. Originally, what I actually did was I estimated a logistic regression model with the sensitivity and specificity as they gave. And then I was noticing, well, wait a second, we were getting some weird results when we were applying to the 2005 data. And the reason being is because when we do this computer simulation where we're simulating the 2005 outcomes, we have to assume the outcomes that they have given us are correct. And to get that correct relationship between the covariates then with piece of I in 2004, we have to unfortunately make the same. There's a better way to do it, I'd like to know. Because of course you want to make this as realistic as possible. Yes?
So it's a sort of unrelated thing, but when you're maximizing a function with a very simple method computationally, and you have a range, instead of sort of splitting in halves to check whether you've got the maximum so far, you might do a golden ratio search. So you look at 0.61, whatever, and it's much quicker. Well, not much quicker. It's quicker at getting to the maximum.
Okay.
Halves. So I wonder whether that golden ratio might be useful for you instead of halves.
I will bring it up with my graduate student because we did have some difficulty, showing that aspect, truly. But yeah, thank you for bringing that up.
It's advantageous to just get it away from half. Yes, yeah.
Okay, thank you. Yes.
So, yeah, that last step seems kind of frustrating. We have to get down to finally testing each individual.
Yeah.
Are there situations, I'm thinking of the prevalence again, where it makes sense to do sequential testing, especially for something you're sure is quite rare. So there's a really good chance that if the group is positive, there's just one individual, or you're willing to live with the risk of not capturing everyone.
Well, a lot of the earlier research, or I guess some of it, often made the assumption that, okay, you only have one positive, because typically when these groups are constructed, since it's a rare outcome, you're only going to have one positive. And if you could do that, sure, that would lower the number of tests. At least I'm not necessarily comfortable with it, especially with what we're finding that all of our informative retesting procedures work better for the higher prevalence cases. And then to some respect, it actually allows one to do group testing in situations where you wouldn't have done group testing in the past. So if you have these higher prevalences, now you're starting to have more than one positive in a group, and that starts becoming a problem with that. So, and still, eventually at some, I would hate to, I don't know, maybe this is my bias of how this would be done. I would hate to declare someone positive without actually doing an individual test on their particular specimen in the end. Unless I misunderstood you, that's what potentially could happen. And I think what you're saying, that's perhaps that's based upon what we've seen so far in a sequential manner, yeah, this person's most likely positive.
How about if you don't prevalence rate, and what you would like to do is test the prevalence rate after you have done this?
Well,
of course, if your SDE and SP are both one, you don't have any problem because you know exactly
Yeah.
what to go on. But what if you don't have SDE and SP equal to one? So you just couldn't take the ratio. maybe it becomes biased because it depends on how SE and SP are related.
Okay, so you're, if I understand your question, you're talking about estimation.
Estimation.
Okay. I mean, yeah, I mean, we're primarily obviously just concerned about the classification problem, group testing versus the estimation problem. And I know there's been some previous research done where basically, if they're doing some of these retests, it's not going to help a whole lot in estimating the overall prevalence. Just do one set of group tests. And there's simple ways that you can incorporate sensitivity and specificity into that corresponding estimation. So.
I think it makes sense to incorporate some ideas from like adaptive design. So in terms of maximization once, do maximization each time.
Could you give me an example of what you mean by adaptive designs?
So I suppose you maximize optimization, you only do once for myself.
I'm sorry, say that again, please.
So I'm thinking you do the optimization probably only once for the whole design in terms of the group size and stuff.
Okay, in terms of doing group sizes and stuff, yeah. And that's some stuff actually Chris has worked on in terms of he adaptively decides on what the group sizes are depending upon where he is in the group testing process. And so that you could have unequal group sizes amongst the, let's say, the population of people that you are screening. So you could do that. We did not necessarily consider that here yet. I would imagine that eventually, in some of the future work that I mentioned, that basically we will be able to adapt to what the group sizes should be based upon what we see for our, let's say, p-hats in the actual application.
Okay, let's thank our speaker.
Thank you.
And we'll have seminar treats and snacks down the hall and